Hello, welcome back to Introduction to Astronomy. Today we are on paper. So pause the video, go grab some paper and a pen, and I'll see you back here. Welcome back. Today we are using Newton's law of gravity. As a tool. And so let's go over exactly what is Newton's law of gravity. Well, as a mathematical expression, it is the force of gravity equals g, gravitational constant, times mass 1 times mass 2 divided by the distance between these two masses squared. As a schematic, let's say we have mass 1, mass 2. If these two masses were still, they were not stuck, there was no other forces acting on them, then the force of gravity, just the existence of mass itself, would cause these two bodies to move towards one another due to the force of gravity. Due to Newton's laws of motion, the force of gravity would produce an acceleration. And so for mass 1, that force of gravity would produce mass 1 to accelerate at acceleration 1. The same magnitude force of gravity would produce an acceleration of mass 2. The acceleration of mass 2 at acceleration mass 2. These would be moving towards one another, but they would not be moving at the same acceleration. If there was one object that was significantly larger than the other, like say the sun in the Sun-Earth system, then the sun would be moving, but at a much smaller rate than the Earth would be moving. One thing I want to point out is the distance between these two items. That's r. And r in the Sun-Earth system is the radius of the orbit of the sun, of the Earth around the sun. Now, as Kepler pointed out with his first law, the orbits of the planets and the moons are elliptical, not circular. But as an approximation, we are going to treat the orbits as circular because it makes the mathematics a little bit easier. So we are making that assumption, that generalization, although it is true that the orbits are elliptical. They're close enough to a circle so we can do some rough first blush calculations by assuming that they are a circle. And so, just to go over that geometry now, if we know the radius of a circle, we can calculate its circumference, which is the length of the orbit, by saying that the orbit length, so we'll call that, the orbit length equals the circumference of the circle equals 2 pi r. And that is a geometrical relationship between the radius of a circle and the circumference of the circle, or the length of the orbit. Okay, so we'll be using that a little bit later. One other thing I want to point out is that if these two masses are not moving at all, there's no other forces in play, there's no other motion, like for example, the planet's not moving at some velocity, well then these two masses are going to move towards one another. The distance between them is going to get smaller, which makes the force of gravity stronger, and therefore it accelerates the masses towards each other even faster. Okay, so the three things to take away is 1, the two masses both accelerate due to the force of gravity, but they accelerate in a way that's proportional to their mass. So massive things accelerate less, the smaller things accelerate more. Okay, so acceleration is proportional, inversely proportional to mass. Okay? And the second thing is As objects get closer, the force of gravity increases. And acceleration increases. All right. Okay, we're on our way. The last thing I want to mention before we move on is how we're going to be using this generally in today's lecture. We're going to be using Newton's law of gravity, some geometry, to discuss how this rule can help us understand free fall on Earth, or maybe free fall to Earth. So without even leaving our planet, we can start to practice and exercise the limitations of this law. The second thing, once we start exploring what this rule means for the behavior of objects here on Earth, we're going to move out to the orbit of the moon. 3, we're going to use the things that we understand from free fall on Earth and orbit on the moon to calculate gravitational constant. And 4, from this, we can calculate the mass of the Earth. And if I haven't run out of room, number 5, we can use all of this to calculate the mass of the sun. With this exercise, I hope to demonstrate that the Newton's law of gravity, plus some astronomical observations and a lot of clever work from many people that have come before us, show the utility, robustness, and universal applicability of this law. This law is true here on Earth, in our solar system, and beyond. The purpose in going through this today is not so you understand and can reproduce all of these rules, and it's also not so you understand every grainy detail. I hope to present to you the thought process that astronomers have used to come to the numbers that today we can just look up. There was never a letter that was delivered to somebody that had the gravitational constant in it. It's the result of people thinking and using these equations, applying them, figuring out what they didn't think of. And so I hope you consider that part of your arsenal and part of your toolkit, that you can look these numbers up, but having a physical sense of where they came from, and also maybe how they could be improved in the future, or where there might be holes, I think is a useful thing to have in your mind. So let's continue. These are our goals for today. Now let's begin with here, free fall on Earth. So right now, we are all on planet Earth for the meantime. Well, the first thing I'm going to do is I'm going to rewrite our Newton's law at the top. Force of gravity equals gravitational constant, mass 1 times mass 2, divided by the distance between those two things. So for me, I have my coffee cup sitting here on my desk. And yeah, we're here on planet Earth. The mass of Earth is pulling everything towards its center. But we're not imploding. Why not? Well, that's because the force of gravity is counterbalanced by a normal force, the force of the table right now pushing back on the cup, that keeps everything still. So the acceleration of this system is 0. The summation of forces equals 0. There's no motion. But if I were to lift my coffee cup a little bit off of the surface of the table and drop it, well, there would be a time when the cup was falling through the air, then it would impact the table at some velocity, and then it would stop moving. So I can use that study. I can incrementally increase the height from which I'm dropping my coffee cup, measure the amount of time it takes to hit the ground, and in that way study how gravity is accelerating my coffee cup. I'm going to stop calling it a coffee cup and I'm going to start calling it a ball. So let's see about this hypothetical study we are going to run. We have distance, that's the height I'm going to raise, let's call it a ball now, above some surface, and I'm going to drop it. And I'm going to use a stopwatch and measure the amount of time it takes for that object to drop. So these are both things that I can measure. And it turns out it doesn't matter the mass of what I choose to drop, which we can talk about later. Any object will do. The reason that experientially you see things take longer to fall to the earth is not because gravity affects heavy things less than light things. It is because of air resistance. And so if you had a round billiard ball that you dropped, let's say a billiard ball that you dropped, right? The air resistance would have an easier time flowing around the ball and the ball would drop faster. If you dropped, say, a piece of paper, that's a greater surface area for the air to act against, and that's why you would see it move in like a fluttering pattern and therefore take longer to fall. If we take out the effect of air resistance and we're just looking at gravity, which we can do more closely with something shaped like a ball, then there's no effect. Mass does not matter. Mass does not affect how quickly something falls. So without a vacuum to test in, if we were to just choose an aerodynamic shape like a ball, we could still run these tests. But so in summary, the mass of an object does not affect how quickly it falls to the ground, not in a vacuum. So time and distance. I've got my ball, 0 meters above the ground. All right. How long does it take to hit the ground? Well, it's already at the ground, so 0. So we start off at 0, 0. I'm going to raise my ball to 1 meter and then drop it. Start the stopwatch when it starts, when I let go. Stop it when it hits. That's going to be about 0.3 seconds. 0.33. All right. Next study, raise. Now we're at 2 meters. Start the stopwatch, drop, start the stopwatch, click, end. It fell 2 meters. If you were to clock that, it would be about 0.45 seconds. All right. So let's draw each of these data points as we log them. All right, let's do one more. 3. Okay, start the stopwatch. When I drop it, it falls. Check the time. It's going to be about 0.55 seconds. Okay. 3. Draw that last data point. So for it to fall 1 meter took 0.3 seconds. For it to fall another meter after that one took much less time. And then for it to fall from meter 2 to meter 3, it's falling even faster. So as it was dropping, the speed was not constant, it was accelerating. But we're going to prove that to ourselves by using this data to calculate the velocity. So we know velocity equals, what does velocity equal? Distance over time equals d over t. So if I turn this into a chart where I have distance and time, my distances are 1, 2, and 3. My time's 0.3, 0.45, and 0.55. Then I can divide 1 divided by 0.3 and get about 3 meters per second. And then continuing, I can keep calculating those other values too. Continue along. If I plot those below my distance and time plot, but instead I'm plotting velocity and time, well, I have the same x-axis 0.3, 0.45, 0.55, but then I have the values I calculated here, right? And so when I plot those, if I were to calculate and plot those, I would have roughly a line. Okay. If I analyze this trend to calculate the acceleration, from the time, again, same time points, 0.3, 0.55, 0.45, 0.55, I would find that the acceleration is constant. And the acceleration equals 9.81 meters per second squared. That is the acceleration produced by an object in Earth's gravitational field. If I come back to my original equation, the sum of the forces acting on the ball equal mass times acceleration. Well, for the time that it's falling, that means it equals mass times g. That gravitational constant here on Earth. Well, what else does it equal? Well, it also equals Newton's law. G times m1 times m2 divided by r. Well, what are the parameters in this side of the equation? Gravitational constant, m1, let's call that the mass of the Earth. m2, that'll be the mass of the ball, that's m. Since m and m2, which I'm calling mass of the ball, are on the same side of the equation, we're going to cancel those two things out. And r is the radius of the Earth. Let's just rewrite this so it looks a little bit cleaner. G is the acceleration I just measured, equals the gravitational constant times the mass of the Earth divided by the radius of the Earth. All right, I just calculated G with my little experiment. The radius of the Earth, we'll talk about how, oh, I think I am off the paper. Okay. Yeah. So G, we just talked about how to find G. The radius of the Earth, if you recall, Aristarchus, here we go, E-R-A-S, one of the ancient Greeks, was able to calculate the diameter of the Earth by looking at the shadows cast by the sun. And we'll go over exactly what that was in brief really quickly, but he is the person to look up if you want to figure out how you can calculate the diameter of the Earth by looking at shadows. But back to our equation. We know G. We just ran an experiment to find that. The radius of the Earth, that's something we can get from observations of the sun and the Earth and the shadows cast on the Earth. Gravitational constant is something we could look up, but let's pretend that we don't know that number. And the mass of the Earth, let's also pretend like we don't know that number. So what we have to start with is remembering back to how the ancient Greeks calculated the diameter of the Earth. So in summary, how that went was an observation made in the Library of Alexandria that on one day out of the year, the columns in a temple would cast no shadow. And that was because the sun was directly overhead. So at high noon on one day of the year, there was no shadows cast by some columns in a temple. Well, many thousands of miles away in another city, on the same day that there was no shadows cast by this column, there was another column that did cast a shadow at the same time on the same day. And so what the ancient Greeks did is they measured the length of that shadow and the height of the column, and then using trigonometry they could calculate the angle between these two points on the surface of the earth. So it's just geometry, trigonometry. By walking from one location to the other, they measured what's the distance between these 2 points. So now we have an angle measured from the center of the earth of these 2 points using trigonometry, and a distance. So using geometry, the angle measured is some fraction of all the degrees in a circle, 360. That is proportional to the distance between those 2 points as a proportion to the entire circumference of the earth. And we talked about the circumference of the earth equaling 2 pi r. So if we can measure d, if on this one special day we can measure theta using shadows, then we know that r equals d over 2 pi 360 over theta, which with those rudimentary experiments, the ancient Greeks were pretty close in thinking that's about 8,000 miles. Oh, I'm sorry, the radius, about 4,000 miles. And that would make the diameter of the earth about 8,000 miles, a little less. But that's pretty close to accurate. So by using trigonometry, being very clever, and calculating the shadow cast as a way of understanding how the curvature of the earth affects, so you can get an estimate for the radius of the earth. Coming back to our other equation. So this told us that g, the acceleration produced by the earth on any object, so acceleration in free fall, times the the radius of the earth, which we can calculate using shadows and timing, equals the gravitational constant times the mass of the earth. All right, so we know this number, 9.81 meters per second squared. We know the radius of the earth is about 4,000 miles, or about 7,000 kilometers. You can convert between those two. Now, we don't know gravitational constant, or let's pretend like we can't look it up, and we don't know the mass of the earth. Well, there was times when people didn't know either of these two things. How did they figure it out? Well, we want to understand the mass of the earth. So if we think about something else that would orbit the earth, what would tell us, what else could we study that orbits the earth and is subject to gravity, that we could analyze the motion of, that might tell us something about gravitational constant or the mass of the earth? What's maybe a satellite of the earth, a natural satellite of the earth that's subject to gravity and under the pull of the mass of the earth? Well, the moon. Okay, let's flip back to our original work plan. So we talked about free fall on the earth, and we found that every object is pulled towards the earth at the same rate of acceleration, 9.81 meters per second squared. Okay, that's true on Earth. That's not true on other planets. Other planets have different values for that based on their mass. But on Earth, that's true. And we can take measurements to calculate that number. Let's look at the orbit of the moon. Okay, so let's find a new page. Let's draw a diagram. The moon orbits around the Earth. Let's use the drawing in a roughly circular orbit. We don't know the radius of the orbit. We do know the radius of the Earth from the shadow work of the ancient Greeks. Well, let's look at our equation and see how much we've got to figure out still. Force of gravity equals our familiar song, gravitational constant times the mass in this system, the mass of the Earth times the mass of the moon, divided by the distance between them squared. Well, we talked about the fact that if these two bodies had no other forces acting on them, then they would move towards each other until collision. But they don't do that. The moon's orbit is fairly stable. The moon's orbit is not as stable as the Earth's orbit around the sun. The moon is slowly moving away from the Earth and eventually will lose the moon, but it's in a fairly stable orbit that we can approximate as stable. But the moon's not coming towards the Earth, so what force is pushing it away? Well, that force is called centripetal force. So if we draw the forces acting on the moon, we have the force of gravity pulling the moon towards the Earth, and we have a centripetal force produced by the velocity, the motion of the moon, which is pulling it away. And the balancing of those two forces is what keeps it in the orbit. So that's going to be called force C, or centripetal force. Okay, let's write that as an equation. Force gravity equals force centripetal. Well, what's centripetal force? What's the mathematical expression for that? Force centripetal equals the mass of the moon times the velocity of the moon squared divided by the distance between the moon and the Earth. So we'll call that R. All right. Well, what's the velocity of the moon? Well, the velocity of the moon is, if we take from our other definition, the velocity is the distance the moon moves over time. Well, what do we know about the distances the moon moves, or the times? Well, we know the orbit. From watching the orbit, we can see that the time that the moon takes, the distance the moon orbits, is a function of the radius. The circumference of the orbit, or the distance of the orbit, is equal to the radius times 2 pi. So every 29 days, the moon orbits around the Earth a distance 1 radius away, and the total length of that orbit is 2 pi r. Okay, so we haven't introduced any new variables, and we've changed this velocity variable into a variable that's already in the equation, r. Now it's time to put our new expression for velocity, 2 pi r over big T, which we know for the moon is 29 days. For the moon orbiting the Earth is 29 days. But that's a known number that we can plug in later, so it doesn't add any confusion or complexity to our equation. Okay, so we know the expression for velocity, we know expression for the centripetal force, and the force of gravity. Let's put these three things together. Let's combine equation 1, 2, and 3. So the force of gravity, G, times the mass of the Earth times the mass of the moon divided by the distance between them squared is going to equal centripetal force. So the mass of the moon divided by r times the velocity squared, which is 2 pi r squared, 2 pi r divided by t, that entire thing squared. So we can cancel some terms out. The mass of the moon is on both sides. The r in the denominator cancels out the square in the gravitational term. So if we write that below, try to simplify all this stuff, we leave with the gravitational constant times the mass of the Earth equals take this r, multiply it over here, r cubed 4 pi squared all over t squared. All right. So now we have a similar equation, a term g times the mass of the Earth. Here, g times the mass of the Earth equals two numbers we know, 9.81, which is meters per second squared, which is the acceleration caused by the mass of the Earth, and the radius of the Earth. So we know these terms. And here, we know these terms. So we could set, so we know GME, gravitational constant, times the mass of the Earth equals the acceleration produced by the Earth times the radius of the Earth. Okay, so we could set this equal to this, and because we know t squared, 29 days, we know pi, we could solve for r, which is the radius of the orbit between the moon and the Earth, using this expression. But the way astronomers figured out, or another way they figured out the distance between the moon and the Earth, so we could do it all with calculations by setting the centripetal force and the force of gravity equal and canceling terms. The other way was observing the moon during an eclipse. And so during very particular times, the moon, let me just find a new page for this. Okay. The moon and the sun and the Earth, right? But let's just look at the moon first. The sun will be in such a position as to illuminate half of the moon. And so from the Earth's perspective, if you take a look at from the Earth's perspective, if you keep a careful eye on the moon and the phases of the moon over its 29-day orbit, you can catch a time where the moon is half illuminated by the sun and half not illuminated by the sun. At that point in time, it means the light coming from the sun is coming from 90 degrees away. So the light produced by the sun is coming in, illuminating half of the moon as observed by the Earth, and you can catch that time if you're very observant of the moon, when it's half lit and half not. What that allows you to do is draw a right triangle between the center of the Earth, the center of the sun, and from the center of the sun to the center of the moon, and the center of the moon to the center of the Earth. Because there's a right triangle here, because half of it is illuminated, half of it's not, what you can do is, again, measure the angle cast by the sun. That tells you the angle of this side of that right triangle. And so you know the distance from the Earth to the moon, and also if you know the distance from the Earth to the sun. I apologize, but this is a little premature. It was a slightly different piece of work to calculate the distance from the Earth to the moon. Okay, so let's try something else. All right, so where we were talking about unknowns of gravitational constant, unknowns of the mass of the Earth. These are unknown. What we do know is the acceleration created in Earth's gravity well. Under free fall, we can measure that. The radius of the Earth, can measure that by looking at shadows. The ancient Greeks had various accurate estimates of that. We know the time it takes for the moon to complete one orbit. We know pi, we know 4. So we could set these equations equal to each other and find the radius of the orbit from the moon to the Earth. But if we do that, then we still don't know what the gravitational constant and the mass of the Earth are. So if we can find another way to estimate the distance between the moon and the Earth, then we could use these equations to find, we have two equations and two unknowns, we can calculate the gravitational constant and even the mass of the Earth. Okay, so let's see if we can use astronomy to figure out the distance between the Earth and the moon. And there's such a time where the sun and the moon and the Earth align. So the Earth blocks the sunlight from getting to the moon. By timing, so the sun, let's take this as a time lapse. The sun is shining on the moon, and the Earth is moving around the sun, right? Let's say the moon is moving too. So the moon is completely illuminated, right, or partially completely illuminated. As the Earth moves, there's some times where things line up, where the Earth moves and casts a shadow onto the moon itself. By watching how long the shadow is cast on the moon, and knowing the size of the sun, you can estimate the distance between the two bodies. So the time between the time that the Earth eclipses the moon is about 3 hours, 2.53 hours. The total time that the moon takes to complete one orbit is 29 days. Another piece of information is that the Earth's diameter is about 8,000 miles. And the moon's orbit is 2 pi times the radius of the orbit. So by analyzing these ratios of how long the moon was blocked, calculating the width of the Earth, how large the Earth's shadow was on the moon, and looking at how much of a percentage that was of the total orbit, by playing with those percentages and those ratios, you can roughly estimate the radius of the orbit of the moon to be about 60 times the radius of the Earth. Right? So 60 times 8,000. So if we plug that in, the radius of the orbit of the moon around the Earth roughly equals about 60 times the radius of the Earth. Now this becomes a number. This is 60 times 8,000 times 4 times 3.1415 squared divided by 29 days squared. And if we get all the units right, then we come out with a number. Okay? And the same thing on this one. On this side, 9.81 meters per second squared times 8,000 or 4,000 miles for the radius is going to also give us a number. Because we have two equations and two unknowns, we can figure out what the gravitational constant is and even what the mass of the Earth is. And although those details may get fuzzy, I want you to understand that this coupling of Newton's law and trigonometry, careful observations of the sky, all lead to the estimates that we have about, say, the mass of these celestial bodies. And because the universal law of gravity does not only apply to our system of how things are attracted to Earth, but can be applied to the moon, even to the way the planets move around the sun, that generalizability, that universality of these rules allows us to extrapolate and make all kinds of estimates. So let's return to our original agenda. Free fall on Earth, that acceleration is always the same. orbit of the moon. We can use scrupulous analysis of the motion of the Earth, of the phases of the moon, and the shadow cast by the sun, and the phases of the moon. We can use those observations to use those observations and also geometry to calculate the distance between the moon and the Earth, which lets us calculate the mass of the Earth and the gravitational constant. And because those rules are generalizable, then we can use other observations of the sky to estimate the distance between the sun and the Earth. And that is what I started to do with this diagram. Once we can estimate that the distance between the Earth and the moon is about 60 times the radius of the Earth, then we have this leg of the triangle. If we catch the observation at just the right time and can calculate the angle between the Earth and the sun using shadows, well, then we can say the hypotenuse, the distance from the sun to the Earth, d, is equal to, using trigonometry, 60 times the radius of the Earth times the cosine of theta. And that allows us to roughly guess what the distance is between the Earth and the sun. Coming back to our Newton's law, the force of gravity equals g, mass of, say, the sun, times the mass of the Earth, divided by the distance between them, which we can calculate, which becomes a number. If we set that equal to the centripetal force, we again get an expression for the mass of the Earth times the velocity squared over the distance between them, again d. Sorry, this d is squared. The mass of the Earth drops out. We can put v in terms of the distance between the Earth and the sun and the time it takes for Earth to complete one orbit, all things that we know. The distance between the sun and the Earth are things that we can calculate. We've figured out an estimate for a gravitational constant based on the analysis of free fall on Earth and on the moon. That lets us estimate the mass of the sun. Similarly, we can estimate the mass of Jupiter by observing the way the moons move around Jupiter. But I hope that that was an introduction. So with that, I'm going to conclude. I hope that was an introduction to the way that you can use trigonometry, astronomical events, Newton's law of gravity to predict the motion of things in our solar system and extrapolate them out further. Congratulations for getting to the end of this video. I really wish that we were together and we could work on this stuff together. I could answer your questions in real time and clarify things, but I really appreciate your patience. I'd encourage you to reach out with questions or look up online for clear tutorials about how to work through these proofs and how you can do some of these astronomical measurements and calculations and use physics to do things like estimate the mass of the sun, estimate the distances to the moon and the sun on your own. Thank you very much. I really appreciate you working with me. I wish we could be together to work through this stuff together, but thank you very much and looking forward to talking to you soon.